we're going to look at geometric sequences. And this is the general formula for a geometric sequence. And it's very similar to a basic exponential function, where you have your f at x is equal to, and a stands for the y-intercept in the exponential function, and here a is known as the first term. Okay, so it's the first term in your sequence. B is usually the base of the exponents, whatever it's increasing by, and in this case that's our R value, and R value is the common ratio, so what it's changing by, and that's pretty much what exponential functions are growing by. And then in an exponential function, b will be to the power of x, and our x is kind of broken into two numbers, a variable subtracted by the number 1, and n is just the number of the term. Okay, now the only last thing we have is term number. So Tn is the term value. So whatever, if it's our fifth term, what is the number for our fifth term? And if we're talking about the fifth term, that's when n is 5. So we'll kind of try to set that up here. So they've given us a sequence here, and we're going to try to build the formula out of it. The first thing we need to figure out is what is this formula changing by each time we move numbers, and we assume it goes on continuously. Are you able to tell what this changes by?
Divided by 2.
You're right, it's divided by 2. Now, the problem is, or not that it's a problem.
Multiply by a half.
Yeah, we usually multiply. So instead of dividing by 2, we would just say multiplying by the half. It's the exact same idea, right? So anytime we're dividing by a whole number, we can just multiply by the reciprocal of that value, right? So if we're dividing by 2, we multiply by, instead of 2 over 1, we multiply by 1 over 2. It does the exact same thing.
So if there's any number, like 6.
Yeah, so if we were multiplying by 6, if we were dividing by 6, then you can also say we're multiplying by 1 over 6. Same concept, okay? So with that being said, that means that's our common ratio. So our R value, our R value is a half, okay? A is the first term, which is pretty straightforward. They've given us the first term. It's not like we had to build up to it and we have to go back. They've told us our A value is the number 4, okay? And really for the general formula, that's it. We don't have a value for our term number, or we don't have a term number. We really just need the R and the A. So if we're going to build this formula, any term number, this is the general formula, any term number is equal to 4 multiplied by 1/2 to the power of whatever term number we're looking for, subtracted by 1. Okay, and that would be the general formula. And then from there, let's say they then asked us, what is the 15th term? Okay, now we only went 1, 2, 3, 4, right? So that's a long way to go to continuously multiply by half, where in this case, we can just plug it into our formula. If we want to find the term number for the 15th term, our term number is equal to the number 4 times a half, and we have 15 minus 1. So it's actually going to be to the power of 14, okay? So when we do that, we can take out a calculator, and we're looking at a half, 1 divided by 2, and we're going to get a decimal value. I'm going to make this a fraction after, to the power of, I hope it's going to fit. It's a really long term. Ooh, yeah. And then times 4. Okay, so there would be our term value as a decimal. Kind of inaccurate, okay? And since it's a fraction, I can show you another way to go about doing this. We'll leave it in fractional form. What we'll do, I'm just going to move the other question down just a little. We'll get to this after, so we have a bit more room. Let's think about when we're multiplying fractions. Our term number is equal to 4. And again, it's to the power of 14. Well, if you think of your distributive property, you can technically put 1 to the power of 14 and 2 to the power of 14, okay? The 1 to the power of 14, so we got our 14 and we kind of distributed it to the whole fraction. 1 to the power of 14 is just going to be 1. It's going to make absolutely no change for us, okay? So we still have 4 times 1. And then we can figure out what 2 to the power of 14 is, and we'll have just a very large fraction instead, and that way our answer is going to be extremely accurate rather than some, not repeating, but some decimal that's constantly changing. And this, technically, this isn't completely accurate, though very, very precise. 2 to the power of 14, okay? 16,384. So now we have 16,384, okay? And then to multiply 4, we just do 4 times 1. So the 15th term, and I should have been writing that in for the end value, the value of the 15th term is 4 over 16384, whatever that would be, and that's that really long number we discovered. Okay, so once we have the formula, we can kind of work through it. Now, our second example. This is a much harder example. Okay, they've given us two term numbers, and they want us to build the general formula again. So again, the general formula is t at n is equal to a r the power of n minus 1. Okay, let's build parts of the formula with the information we have. And then, like when we're solving linear equations, okay, we're going to kind of put the two formulas together and use the idea of substitution. So, first term number, t at n is 5, okay, is 18. So we're going to replace term number with negative 18 is equal to a times r. The n we know. This is the n value. The n is the number 5 there. So it's 5 minus 1, which means it's the 4. Okay, we've got it. And in the next one, we have 27 is equal to a times r. And the term number, again, we know it's 6. 6 minus 1 is 5. Great. Now, here's the problem. We have two variables. So this is going to be hard to solve. But I can actually figure out the common ratio. Because these are consecutive terms, this is the 5th term and this is the 6th term, it's one after the other, I can take the 6th term and divide it by the 5th term to figure out what the common ratio is. The same way we could have done it here. We could have took 2 divided by 4 and we got a half. That was the common ratio. Okay. Views fractions just because it's a little harder to work with. So we're going to take 27 and we're going to divide it by negative 18. It'll give us some repeating decimal number, I think, or maybe just 1.5. But let's turn it into a fraction. I know I can divide both of these by the value of 3. So this is going to give me 9 over 6. In fact, not only can we divide by 3, let's divide by 9. That'd be even more helpful for us. 27 divided by 9 is going to give us 3. And negative 18 divided by 9 is going to give us negative 2. So our common ratio is negative 3 over 2, or negative 1.5, okay? Whichever way you like it. I'm going to keep it as a fraction just so we're pretty accurate. So that means our r value is equal to negative 3 over 2. So now let's replace our r value with that. So we have negative 18 is equal to a negative 3 over 2 to the power of 4. So I'm going to work that out as a fraction. And over here, we have two equations. 27 is equal to a negative 3 over 2 to the power of 5. Okay. Because we have an a in both formulas, we're eventually going to substitute an a into the other one, and we're going to use it to solve. Actually, hold on. We don't even need to do that. I don't know what I was thinking. We can actually just go about solving this. We can isolate for a in both of these. Because we had two formulas, two variables above, we would have done substitution. We don't even need to do that, I just realized. We can just isolate for a and figure out what the first term is. We can isolate in both just to make sure it's the right one, but the a should be the exact same. I'm not sure why I thought we had to do substitution when I first looked at this. Anyways. Yeah. Okay, so let's go. Negative 18 is equal to a. Here we have negative 3 to the power of 4. Okay, so because this is a positive exponent, an even exponent, I know that a negative times a negative times a negative, it's going to be a positive number. So we're going to do 3 to the power of 4. It will end up as a positive number, is 81. And 2 to the power of 4, I think it's 16. Yeah. So we're going to have 81 over 16. Okay. And over here, we have 27 is equal to a negative 3. It's going to be 243, I think. Let's see. 3 to the power of 5. Okay, 243, but it will be a negative this time. Yeah. So I have negative 243, and then 2 to the power of 5 is 32. Okay, that's an a. When we divide by a fraction, it can be confusing. Think of it like, we have a negative 18 divided by 81 over 16. And then we kind of set up, negative 18 divided by 81 over 16. Then we reverse and we do all kinds of stuff. Then one of the easiest way to do this is just to make this multiplication and flip the fraction. Okay. So when it comes over, we'll have negative 18 times, and we just invert it, 16 over 81. And then we can go right into that multiplication. It's like a quick way to do it. Okay. So we're going to end up with 18 times 16. 288 is going to be negative. So 288 over 81. So negative 288 over 81 is equal to A. So whatever this is, let's find out. Negative 288 divide 81. There's our number, negative 3.5, repeating. That was our first term. Let's see if that's the case over here. 27, again, we're just going to invert it. 32 over negative 243. Okay. It's going to be equal to A. And we'll end up with some fraction. 27 times 32. 864. 864 over negative 243 is equal to A. Let's see if these values are the same. And we could do the same by like reducing the fractions to see if they're equivalent fractions, but this is a quick way to check. 864 divide 243, and we know it's going to be negative, whatever our answer is. 3.5 repeated to 6. So there you go. We end up at the exact same answer no matter which of the two formulas we used. Okay.